the simplest of all these addressing modes is the register addressing mode. So, here the operands are registers. So, most of the operations that we have in 8086 they are 2 operand instruction. So, where apart from the opcode we will have 2 operands on which through which the operation will take place. So, the instruction will specify the name of the register which holds the data to be operated on by the instruction, like say MOV CL comma DH. So, content of this DH register will be moved to CL register. So, both are 8 bit registers. So, there is no problem. So, CL gets DH. So, this is an example of this register addressing mode. Then we have got immediate addressing mode. So, in immediate addressing mode, so the second operand that we have is an immediate value. The first operand may be is a register, whereas the second operand has to be an immediate value. So, this immediate value can be 8 bit or it can be 16 bit, that depends. So, there should be a match, like if you are specifying an 8 bit register here, then this value should also be an 8 bit value. If you are mentioning a 16 bit register here, then this value will be taken as a 16 bit value. So, this MOV DL comma 08 hex. So, this 08 hex will come to the DL register, that is a 8 bit value, and MOV AX comma 0A9F hex. So, this 0A9F hex will come to the AX register. Out of that, this 0A part, so this will go to the AH register, and the 9F part it will go to the AL register. So, that way this 16 bit value will be divided into higher order byte and lower order byte, and they will be going to different registers. So, for memory access, so we see that 8086 has got 20 address lines. So, these address lines are they can address up to 2 power 20 equal to 1 megabytes of memory. However, the largest register is only 16 bit. So, to get this physical address, so this actual address is calculated the actual address of a byte in memory, that is the value of that goes out on the address bus, that has to be calculated, and that is the physical address. So, how is this physical address represented? This is represented in the form of a segment value and an offset value. So, 89AB colon F012. So, what will happen is that this 89AB, so this will be left shifted by 4 bits. So, that way in a hexadecimal form. So, if we write, so as if a 0 will appear at the end. So, it will become a 20 bit value. So, this is a 20 bit value, each digit corresponding to 4 bits, the 5 digits. So, the 20 bit, and this F012. So, this is the offset part. So, F012 is taken as a this is also a 16 bit value. So, we take it as a 20 bit value. So, most significant digit in hexadecimal notation becomes 0, and then you do the addition. After that you get a 20 bit result. So, that will be that will be the physical address. So, physical address is the address, the actual address of the byte for the physical memory. So, it will be doing this memory access will be done by doing this operation. So, this 89AB F012. So, these quantities can come from different registers, like if you are writing like if you are using say the SI register. So, SI register contains F012 and DS register contains 89AB. Then when you are saying that MOV AX comma within so if you are writing like say MOV AX comma within bracket SI, then we assume that this 89AB. So, this is in the DS register and this is in the SI register. So, this is what will happen internally, and then on the address bus, the address that will be put is 98AC2 hex. So, that way the operation takes place. Next, we look into the different addressing modes. First one is the direct addressing. So, in case of direct addressing, the address is directly provided in the instruction itself. So, the address of the memory location is given in the instruction itself. The effective address is a 16 bit number. So, this is the 16 bit number that we have. So, 1354 hex. Okay. So, this is the 16 bit number, or 0400 hex. So, that is a 16 bit number. So, this square bracket that we have, this square bracket. So, they will identify that we are interested in the contents of those location. So, if these are not there, that means they will tell that is actually the immediate addressing. Okay. So, that is the convention followed in 8086 assembly language. So, if these square brackets are missing, then that will mean an immediate data. If the square brackets are there, it will mean that it is an address. So, it will be accessing the corresponding memory location. So, when executed, this instruction will copy the content of memory location into the BX register, and then so in this case, in the first instruction, what will happen is that this BL register will get the content of memory location 1354 hex. So, that will come to 1354. So, that DS colon should be there, sorry. This is not 1354. I cannot say exactly what is the location content, but that is DS into 16 plus 1354. So, that location content will come to BL, and the BH register will get content of memory location DS into 16 plus 1355 hex. The next memory location content will come to the BH register, okay, because this is a 16 bit data movement, whereas this instruction. So, this is a this is 1 byte data movement. So, BL register will get the content of memory location 16 into DS plus 0400. So, this is called direct mode, because the displacement of the operand from the segment base is specified directly in the instruction itself. So, that is the direct mode of operation. Next, we will look into something called register indirect mode. So, register will be used to give the address whose content will be accessed by the processor. So, in register indirect mode, so name of the register which holds the effective address will be specified in the instruction itself, like we are writing like MOV CX comma within square bracket BX. So, this effective address is the content of the BX register. So, this BX register whatever it is holding, so that will be the effective address, and the base address is DS multiplied by 16, and the actual memory address, the physical address that is generated is this base address plus this effective address. So, they will be summed up and we will get the actual memory address. So, this way it will be operating, and ultimately the CX register will get the content of this memory location whose address is given by this MA memory address, or I can say that CL will get the content of MA and CH will get the content of MA plus 1. So, this is how this register indirect mode is working. So, this BX register is used as the indirect as the base register, as the offset register that can be used for accessing the memory location. Then in based addressing, so this is another type of addressing which is similar to your indirect addressing, but this BX or BP register they can be used for holding the base value and the effective address, and then signed 8 bit signed or unsigned value or 16 bit displacement that will be specified in the instruction. So, the signed 8 bit or unsigned 16 bit displacement can be specified. So, this is a typical example like MOV AX comma BX plus 08 hex. So, along with this base register BX, we are also specifying, we can also specify an offset. So, if the offset is not there, then of course, this BX will be used as the base register, and then this will be accessing AX plus this DS into 16 plus BX. But if you are specifying some offset, another offset, some displacement, so that displacement will also get added. So, first of all, this 08 hex, this is an 8 bit number. So, this is extended to the 16 bit, sign extended to 16 bit. So, you get 0008 hex, and then this EA gets BX plus 0008 hex. So, this effective address that we get, so that is BX plus this value. If the content of BX is say 1000, so after this addition the EA, the effective address will become 1008, and then this base address is DS into 16, and the memory address that is generated is this base address plus this this base address plus this effective address that we have. So, then this MA register, sorry, this AX register will get the content of memory location whose address is this memory address MA, or you can say that the AL gets the content of MA and AH gets the content of MA plus 1. So, So, if say Bx is say equal to 1000 hex, then with this 1000 this 8 is added. So, this becomes 1008 hex, and then it depends on the DS register. So, if DS location content is say 2000, then this 2000 hex. So, this 2000 is left shifted by 1 bit or by 4 bits. So, it becomes this one. With that this 1008 will be added. So, it is 21008. So, that particular memory location will be accessed. So, this is that memory location 21008. So, this location will be accessed, and this is the MA, this MA equal to 21008. So, this MA, that is the memory address. So, that location's content will be accessed, and that will be going into the EX register, AX register. So, that location's content will come to the AX register. So, this way we can have the based addressing mode, and you see instead of BX you can also use BP, but if you use BP then this stack segment register will be used. So, here instead of this BX, if I use BP, then the modification that you will have is this one instead of being DS. So, it will be SS, the stack segment register. Okay. And otherwise it is same, otherwise the execution is same. Then we will look into the next addressing mode, which is known as the indexed addressing mode. So, indexed addressing mode, it uses some index register to access the memory. So, this SI or DI register is used to hold an index for memory data, and a signed 8 or 6 unsigned 16 bit displacement can also be specified. So, you can say something like this. So, the basic form is like so where the displacement is not there. So, the basic form is like say MOV CX comma within bracket SI. So, there, so you see that all these modes, so they are some sort of modifications of this immediate the indirect addressing mode, but they have been given different names because they have got some specific usage. Okay. This source index register, destination, they are thought to be working as index register, and they are useful when we are doing this string data transfers. So, that is why they have been put into separate mode, okay, this SI and DI. So, in this particular case what will happen, you can understand that CX register will get the content of memory location whose address is given by 16 into DS plus SI. And in this example we have got some additional offset specified, additional displacement specified. So, that displacement will be added. So, this is sign extended. So, you see that the this particular number A2. So, A2 means that if you take that 8 bit notation, then A means 1010 10 and 2 is 0010. So, in that 8 bit notation, this most significant bit is 1, most significant bit is 1 means this is a negative number. So, first before doing the addition, the SI plus 0A2 hex, so this is extended to 16 bit. So, for 16 bit extension, what is done, this most, so this bit is made 0010, the 2 part, and this part is 0100 0101, that is all right. But since this is negative, so this 8 bit that we have, so that is made negative. Okay. So, all these this sign extended. So, this the sign extension. So, all these bits will become 1. So, that it represents the same number A2 hex in 16 bit notation. So, that is the sign extended form of this. So, this becomes FF A2 hex, and with that the FF A2 hex will be added with the SI register for getting the offset, and then this memory address will be calculated. Next we have this based indexed mode. So, based indexed mode means we have got this base register plus this index register. So, they are taken together. So, many times what will happen is that you may need to have 2 or more indices, particularly if you are doing say in particular this the 2 dimensional arrays and all that, then this may be useful that we maintain 2 different indices I and j for the 2 different dimensions. And for that purpose, so we can use this this type of double indexing register, double indirect addressing type of thing. So, the effective address is computed at sum of the base register and index register. So, base register is bx plus bx or bp and index register is si plus si or di. So, here also the same thing, that is 0 a hex. So, when you sign extend, so it becomes 0 0. So, 0 a hex is a positive number. So, sign extended form is 16 bit sign extended is 0 0 0 a hex. Then this effective address is bx plus si plus this 0 0 0 a hex. So, the base address becomes base address is ds into 16, because this instruction since si and bx have been used. So, it will be using ds as the segment register. So, it is ds into 16 and the memory address is this base address plus this effective address. And if it is bp instead of bx, if it is bp, then it will be using the ss register as the stack segment register, as the segment register instead of the ds, the data segment register. Next, we will look into string addressing. So, string addressing for doing the string operations. String is one of the very important data type, you can say, because it is used in many applications, particularly for doing comparison. When you have got some data from outside world, so you need to compare, or many a times for in high level programs we have got lot of string manipulation operations to be taken to be done. And if the underlying processor supports this string manipulation directly, then in the software you do not need to do much complex programs for supporting this string. So, overall the string operations will be made faster. So, this was the objective with which this string addressing was introduced. So, this is employed in string operation to operate on string data. The effective address for the source data is stored in SI register, and for the destination it is stored in the DI register, and the segment register for the source part it is DS, and for the destination part it is ES. So, if the typical example is this moves instruction, the moves B, so or moves byte. So, you can write like byte, or you can write like word, etc. So, or in short you can also simply write it as moves B. So, this can also be written in short as moves B, okay, or you can write in full form like moves byte. So, how is it done? Like this effective address for the source is available in the source index register SI. Then this base address is DS register will contain the segment address. So, base address is DS into 16. So, the memory address is BA plus EA. So, base address plus effective address. For the destination part, then for the effective address will be calculated as DI, and this for the destination part this base address is from the extra segment register ES. So, ES into 16, that will give us the base address for the destination part, and the memory address is BA plus EA. So, this is this extra segment effective address and extra segment base address. So, they will be added to get this MAE, the memory address for the extra segment or for the destination. And finally, this MAE will get the memory location MAE will get the content of MA, and after that if DF flag is set, then SI will be decremented and DI will be decremented, and if DF is 0, then SI will be incremented and DI will be decremented. So, as I was telling that if you are moving from source block to the destination block, and if you have got if there is overlapping. So, if your overlapping is such that the overlapping is so this is the overlapping. So, this is the source and this is the destination. Then what you need to do is that this SI value, SI should point to the bottom of the source and DI should point to the bottom of the destination, and from there you should start copying. So, in this case I have to decrement the values of SI and DI after each byte transfer. So, I have to set this DF value to be equal to 1 in that case, and otherwise if the overlapping is in the other direction, in that case I have to set this df value equal to 0. So, that this si and di values will be implemented after every transfer, and we can have this cx register initialized to some count. So, to see how to have how many bytes you want to transfer. So, before calling moves b, so if I say like move cx comma 100, that means the cx register will have the value 100. So, in that case 100 bytes of data will be transferred, will be copied from source to destination, and after every copy this SI and DI registers will be updated to point to the next byte, and this CX register value will be decremented to see that whether 100 byte transfer is over or not. So, when it is done, then it will come out of this moves B instruction. So, next we will look into IO port addressing. So, there are these addressing modes can be used for to access data from standard IO map devices or ports. So, IO mapped IO can be used. So, where the port address is the IO port address, and in or you can have memory mapped IO, where this memory locations are the IO ports are taken as memory locations only, and the simple move type of instructions can be used. So, in direct port addressing, so we can have this 8-bit port address directly specified like this. I can have in AL comma 09 hex. So, this port address is 09 hex. So, on the address bus this 09 hex will be put, and it is expected that the corresponding device will get selected and the value will be available on the data bus. So, at the end, so this AL will get the content of the port whose address is 09 hex. And in indirect port addressing, so some register value will be used as the port address. So, we can specify a 16-bit port address and some register value will have the address. Whatever be the content of this DX register, so that is put on the onto this address bus, and then this AX register will be content will be put onto the data bus. So, that this AX register content will go to the corresponding port. So, this way we can have this IO port addressing, both direct IO, that is having 8-bit address, or indirect IO having 16-bit address via some register. Next we look into relative addressing. So, relative addressing means that with respect to the current program location. So, we are trying to update the instruction pointer to go to the next instruction. So, the effective address of a program instruction is specified relative to the instruction pointer by an 8-bit signed displacement. So, this is like this. So, ZZ 0A hex. So, this will be this ZZ 0A hex. So, this will be doing like this. First of all, this 0A hex. So, this will be sign extended. So, it will become a 16-bit value. Now, if the 0 flag, so the jump on 0. So, it will check the 0 flag. If 0 flag is equal to 1, then the effective address will be IP plus this 000A hex, the extended value. Base address is CS into 16. So, that is good for any code segment access, and then the memory address will be this BA plus EA. So, that will be the finally this will be the memory location. Now, the 0, if the 0 flag is 1, then the program control will jump to this particular address, and if it is not, if the 0 flag is 0, then as if the instruction is not there. So, it will be executing the next instruction that is coming in the sequence. One thing to note here is that this displacement that is specified. So, this is only 8-bit displacement. That means, you can do this relative jumping up to 256 locations, minus 128 to plus 127 from the current location. So, if this is the current location, so this offset is 0. So, from there you can go back by minus 128 locations, or you can come forward by plus 127 locations. So, unlike say ARM processor, where it was plus minus 32 MB, so that was a quite big number, but here it is restricted. So, here it is for relative addressing. So, it is only 8-bit. Of course, we have got other type of branching in which you do not need to be restricted by this 8-bit, but relative addressing is 8-bit. Next, we will look into Next we will look into another addressing mode, which is implied addressing. Like some of the instructions where there is no operand, operands are not needed, the instruction itself will specify the data on which to operate, say CLC. So, this will clear the carry flag to 0. So, no operand is needed, or say halt, or say nop. So, this type of instructions where the operands are not required. So, there it will be that is the implied addressing mode. So, you see that 8086 has got a large number of large number of addressing modes, and these addressing modes are useful in different ways. Of course, actually this started this Intel they started with 8086 with having lots of addressing modes, and later on when processors are being designed, like when you go to for example ARM processor, we have seen that many of these addressing modes have been kept and many of them have been removed. Like when you are going to this RISC feature, then many of the complex addressing mode like based indexed and all that, so they have been removed, whereas this indexed addressing, indirect addressing, so they have been kept. So, that way it goes. So, next we will go to the instruction set and of this 8086 processor, and we will see that using these instructions the addressing modes, these instruction sets can be designed by which we can program this 8086 processor to do several operations.